Hello everyone, we are from group 2 of TMM2234 and our group consists of 5 people including myself. First is Sabrina, Asha, Syahira, Aizrien, Siti, Khadijah, David Lee and Aida, Sofiah. Report explores the round-robin process scheduling algorithm, dissecting its code implementation and assessing its performance with varying time quantum values. Through detailed analysis and visual representations, the report aims to pinpoint the optimal time quantum for specific workload, balancing factors such as average turnaround time, average waiting time, and total interrupts. The insights derived from this study contribute valuable information for system administrators and developers seeking to fine-tune their system for improved efficiency and responsiveness.
Good morning, I'm David. This code stimulates the round-robin scheduling algorithm for job processes. Initially, it will read job data from a text file, which will then prompt the user to input the time quantum for scheduling. It will then calculate and display the average waiting time, turnaround time, and the number of interrupts. So in the round-robin function, we have the initialization of variables. The total number of CPU time for each process is then copied into the remaining time array. A loop will then initialize that will continue as long as there are still processes to be completed. If the remaining time for the current processes is less than or equal to the time quantum, the time is updated by the remaining time. The processes is marked as completed by setting it to its remaining time to 0, and the temporary flag is set to 1, which is used for temporary marking of process completion. If the process still need more time to be completed, its remaining time is reduced by the time quantum, and the time is updated by the time quantum. The queue count, which is context switch counter, is then incremented. If the process has just completed, which means the remaining time is equal to 0, and the flag is set to 1, the count of remaining processes is decremented. The waiting time and the turnaround time for the completed process are calculated and accumulated, and the temporary flag is reset. If the current process was the last one in the queue, it will wrap back to the beginning. Otherwise, it checks if the next process in the queue has already arrived. If so, it moves to the next process. If not, it will wrap back to the beginning. This is to ensure that all processes are handled fairly and efficiently.
So thank you, David, for the explanation of the code. So let's look in the output produced by the code, the execution. So our system prompts the user to enter a quantum time here. So for example, I'll put in a quantum time of 10. It automatically gives out the average turnaround time, the average waiting time, and the number of interrupts. So bear in mind, average turnaround time is the average time for a process to complete from start to finish. For average waiting time, it is the average time a process spends waiting in the queue, while number of interrupts is indicates how often the CPU switches between the processes. Then the system will ask the user, do they want to continue? Which will redirect, if we say yes, it will redirect the user to another prompt to enter a quantum time. So, for example, they want to enter another quantum time, which is 60, the maximum one. So, our system will automatically produce the average turnaround time, waiting time, and interrupts. So, if the user prompts a no for the continue question, our system will provide the names of the members of our groups and ends the program.
Hi, my name is Sabrina Asha and I will be presenting the result summary. So based on the table, It shows the average turnaround time, average waiting time, and total interrupts for the round robin algorithm with different time quantum values. We observe that as the time quantum increases, the average turnaround time and the number of interrupts decrease, while the average waiting time increases. So this is because a longer time quantum allows processes to run for a longer period without being interrupted, which can improve their throughput and reduce context switching overhead. However, it can also lead to longer waiting times for other processes, as they have to wait until the current process to finish its quantum before they can get CPU time. This shows that time quantum is crucial to a scheduler's performance. When time quantum is small, the number of context switches is more likely to be affected. So in this specific case, the quantum time of 35 seems to be a good balance between turnaround time, waiting time, and overhead. It has the lowest average turnaround time, which is 123,128, and a moderate number of interrupts, which is 5,535, and the waiting time is also relatively low, which is 118,778 compared to other time quantum values. Therefore, a quantum time of 40 might be a good choice for this workload if the goal is to minimize both turnaround time and waiting time while keeping the overhead reasonable.
From the evaluation at time quantum 25, the value of average turnaround time and average waiting time reaches its peak, then drops at the time quantum 30. The drop in average turnaround time and average waiting time indicate an improved throughput, even though the number of interruptions in time quantum 30 is still considered higher than the other. In addition, the drop in average turnaround time and average waiting time also indicate improved throughput. For average turnaround time, it increases as the time quantum increases with some fluctuations in between. It initially starts at 123158 for time quantum 5, increases gradually except for some fluctuation at time quantum 15 with the average turnaround time of 123174. It reaches a peak at time quantum 25 with 123204 and slightly decreases at time quantum 30 with 123156 average turnaround time. For average waiting time, it follows a similar trend of increasing with larger time quantum with some fluctuations in between. It starts at average waiting time of 118808 for time quantum 5, rises with some fluctuations at time quantum 15 with average waiting time of 118822, and it peaks at time quantum 25 with 118854 and slightly decreases at time quantum 30 with average waiting time of 118806. The bar charts show that the number of interrupts generally decreases as the time quantum increases. It starts at 27,902 for a quantum of 5 and consistently decreases, reaching 3,980 for a quantum of 60. Based on the bar charts and evaluation made, the most suitable time quantum for this specific list of jobs is the time quantum 15. This is because the effectiveness of round-robin scheduling is measured on several scheduling criteria like the throughput, the average turnaround time and the average waiting time, and the number of interruptions. Picking the most suitable time quantum will maximize the throughput and minimize the average turnaround time and average waiting time, also the number of interruptions. If these three conditions are filled, then it will increase the performance of the round-robin scheduler.
So for the justification, the best time quantum is 25 compared to other time quantum. This is due to the lowest turnaround time and waiting time, which is 123,156 and 11,806 respectively. In an interactive setting, a process reaction time may not be accepted if the time quantum is too large and results is needlessly frequent context switches, additional overheads, and worse throughput if uses a too small time quantum.
As for conclusion, the optimal time quantum identified as 25. It minimizes waiting time for executing 30 jobs, enhancing system efficiency and responsiveness. This choice reduces interruptions, contributing to improved performance. A lower quantum time ensures more frequent CPU allocations, equitably distributing processing time among tasks. This approach minimizes wait times and benefits short tasks, while larger quantum time decreases scheduling overhead. Longer burst time enhance process effectiveness by reducing context switch frequency. Overall, a well-balanced quantum like 25 optimizes system performance, providing prompt response in interactive environment.